afternoon session. So it's my pleasure to chair this first part of the afternoon session. We will especially talk for the beginning of this afternoon about design and application of new material with optical properties. And we will especially start with an innovative talk of Raymond Zeissel. I would like to say a few words about Raymond, because Raymond is a distinguished director of research at Strasbourg, and is really a chemist, molecular chemist, more specifically a coordination chemist who likes challenge, and he really likes to make chemistry for novel applications. And he obtained his PhD in 1982 under the supervision of Jean-Marie Laine. At this time, he was developing a very nice pioneering work about carbon dioxide reduction. He was not probably one of the first to work in this area, which is now very popular. And what can I say about Raymond? He obtained the silver medal of CNRS in 2000. According to Web of Science, he has more than 400 papers. I don't know exactly if I'm true, more or less, 400 papers. And his current research interests are in the field of optoelectronics, biomaterial labeling, soft materials such as gels and liquid crystal, sensing also. And just to finish, according to a very short autobiography that appeared recently in Angewandte Chemie, Raymond says that when he was young, he wanted to be a chef. Finally, he chose chemistry. I don't know if cooking has lost something, but I'm really convinced that chemistry has gained a lot. Okay, Raymond, up to you.
Okay, so thanks a lot for this really keen invitation, and I would like to thank also the organizing committee and Feti Bedioui for this really kind invitation, which do not fit exactly within the frame of electrochemistry, but at the end of my presentation, of course, I will go to some applications using electrons. So our motivation is shown here. So the one which are concerned today are the red one. So what we are looking is really to engineer new stable and luminescent dyes, very important. The idea is to tune the optical properties, meaning the absorption, the emission, the excited state lifetime, the continuals, etc., but also to tune the redox activity in the ground state, but also in the excited state. As applications, so these are the red one, in order to fit, of course, within the frame of this conference, we try to use these new materials in energy conversion processes, in solar concentrators, to favor fluorescence energy transfer, so-called FRET, and to apply this in devices like OLEDs or solar cells. So our source of inspiration is, of course, natural photosynthesis, because as you might know, that in bacteria and higher plants, there are a lot of chromophores, which are mostly bacteriochlorophylls, which are involved. A large number of these dyes are involved in capture the photons and to transfer this to a reaction center. So what you see here is really huge numbers. And in more developed bacteria like cyanobacteria or red algae, all these porphyrin are organized in supramolecular clusters. And when you go deeply inside the photophysics of this kind of natural systems, you can see that indeed the photons, each photon is transferred by 5 to 6 limiting steps with really high efficiency, because almost no energy is lost during these processes. So how nature is working? Nature, as you know, uses chlorophylls, which has an absorption spectrum which is well known, the Sorey band and the Q bands. But what you see here is a gap, an empty gap that nature finds way to fill progressively. So nature uses not only chlorophyll A, but chlorophyll B and carotenes, and even more complicated in order to capture all these photons. So this is something which is, of course, really important. So there is a message. If we go through the literature of natural photosynthesis, you see that you have to design chromophore which has really high absorption coefficient, which are, of course, photostable, highly luminescent, fluorescent, most of the time, in order to promote cascade energy transfer. And this is the way nature, and we are doing the same later on, this is the way to concentrate photon. And then you have to think about how this energy could be transferred, and most of the time you have to have a direction to transfer this energy. And then you have to think about, should we design a zero-dimensional, linear, planar, or even tri-dimensional system, and trying to organize matter in for instance, nanoparticles. So my presentation today is mostly based on half a porphyrin, which is called a body P, which is this complicated name here, but this is what you see here. It's a dipyromethane core. It's a flat cyanide which has been stabilized with a boron center. So there are many interesting possibilities for chemists to modify chemically this core in order to fine-tune the properties, to extend, for instance, the delocalization in order to change the colors. You also have possibility in this pseudo-meso position to graft many functions. And what we bring inside this field, and we find this quite recently, we were able to do the chemistry on the boron, replacing fluoro groups by alkenes or aryl groups. This is a way to stabilize first the dyes, which is really important for application, but also to add supplementary functions. There is also a possibility here, or as you will see, to induce charge transfer within these two positions. So this is a little bit chemistry. This is my first part of my presentation. It's quite easy to replace a fluoro function by an alkene. This is alkene pyrene or alkene with simple phenyl groups. Okay? So it's quite easy chemistry. The yields are quite good. This has not been optimized. You have extra structures here which confirm the molecular nature of what you obtain at the end. As you do see, this is the body P here with the boron, and the boron sits exactly in the middle of the dipyromethane flat core. Okay, the alkenes here you have a tetrahedral arrangement around the boron, and all bonds are normal. So this is for the reason for this is because you have no empty orbital on the boron, so you have not extended overlapping between the alkene, the boron, and the dipyromethane. So this is a completely general feature. A little bit of spectroscopy. So this is our reference compound. So the absorption spectrum is this one. So it's the white one. What you do see, you see something really intense here, which is the first excited state of the dipyromethane core, and you have a second transition here, which is the second excited state of the dipyromethane. When you excite it inside this transition, you get really high quantum yields, steady state emission here, roughly around 540 nanometers. So really interesting dye. The problem, the drawback is when you excite it here, you have emission here really above with 20 to 40 nanometers, telling you that the Stokes shift is really weak, in the order of 600 Rev numbers. So this is a problem. So the reason why we target this kind of chemistry is the following. When you switch from this one to the pyrene, then you have a supplementary absorption here, which is the first excited state of the pyrene. When you excite it in the pyrene, you do not see any residual emission of the pyrene, but you only see emission of the body pyrene. This tells you that you have a complete energy transfer from this excited state to this one, and this one emits relaxed to the ground state by emission of light. And now what is important, that Stokes shift is really big. So this is exactly what people are interested in bioanalysis, for instance. So now a little bit of chemistry. Because of this alkene chemistry here, we were able to substitute the 2-fluoro. So I will go really fast on this. It has been published. So then you can do chemistry and, for instance, construct a pyrene on one of this position with a really good yield. So here it's an alkene which is protected. Then you can construct a perilene fragment on this position here. You get these molecules, and here you can deprotect these to a terminal alkene and cross-couple these to fluorine. And eventually you end up with this complicated molecule which have different models. I will show you now the absorption spectrum. Now it's getting different and quite interesting, because as you see here, the absorption of this molecule is really interesting. You, in between 270 nanometers and 520 nanometers, you have a transitions due to the absorption of these different models. And if you excite it in one or the other transition here, all the energy is channeled by a really efficient process to the body pile, which is the only species which is emitting. Of course, you have some residual emissions of the different models if you use picosecond times spectroscopy, and with this kind of information we were able to calculate, to determine in collaboration with Tony Harriman at the University of Newcastle all the weights. Here there is a problem, of course. If you have pyrene which emits, you have seen that pyrene has an emission which overlaps with the second absorption of the body P, but also has an overlap with the absorption of perilene. So you have two ways to transfer the energy from pyrene to the body Pi, either the direct way and emission of this one, or through the absorption of the perilene, which then transfer the emission to the body P. And you see this rate is picosecond measurement, so it's really fast and really efficient. So the question is, of course, as you have seen before, the absorption here is in the near UV and near UV. Okay? The question is, would it be possible to do exactly the same in the visible? So the question is it possible to tune the color of the dyes just by changing the chemistry? This is possible just by switching from pyrrole to isoindoles, for instance, or constructing here double bands with a type of carotene system in these 3-5 positions. This indeed is absolutely possible, and I will show you some examples. So this is our starting material. So this is fluorine, a well-known starting materials. We were able to, of course, cross-link one red dye here, which has an absorption. As you recognize, this is this one. So absorption around 520 nanometers. We were able to construct this dye, which has a kind of pocket, and people know that we are also interested with transition metals. So this is absolutely something which is nice to complex metals, and eventually to tune the optical properties of this dye. But this is another subject. This one, you can then cross-couple this to this one, and you can end it with a compound which has 3 models, one red one and one blue one. The blue one has an absorption around 610 nanometers, and this is the absorption of fluorine. So nothing really interesting here. Of course, the absorption of this molecule is a linear, almost a linear combination of the absorption of the fluorine, the red one, and the blue dye. Of course, we target this one because you see this phenyl group forces the system to be almost orthogonal, to the body P to be almost orthogonal to the phenyl for all steric reasons. This has been confirmed by X-ray diffraction on single crystals. So this is the steady state emission of fluorine. This is the steady state emission of the red one. This is the steady state emission of the blue. You see, we are not far away from near infrared here. So when you excited the complicated molecule with the 3 models, then what you see a little bit residual emission of the red one and a big emission of the blue one. Okay? You do not see any emission from the fluorine. By transient absorption spectroscopy, so here we excited at 400 nanometers. So we excited the red one and the blue one together. So you expect a bleaching of both partners, the red one and the blue one. And this relax back to the ground state in roughly 130 picosecond, and this one in 160 picosecond, really fast. And this is the absorption of the blue excited state, which then relax to the ground state in roughly 170 picosecond. This allows you to determine the rate of energy, singlet energy transfer from one module to the other one. So it's roughly this number. This is also in keeping what you can calculate using some equation like the Forster equation, which is a resonance mechanism. Another way to tune the color is the following. This is the red one, so this is the absorption, this is the emission, 540 nanometers. The blue one with two stereo groups here. So with a phenyl, you see this one is now blue. It emits in the red, 650 nanometers. If you increase the delocalization, for instance, by switching a methyl to a dimethylamino, you have a lone pair on the nitrogen, then this dye is green and it emits in the near infrared. You could not detect this with your eyes. So this is a quite interesting way, so I will not go through all this chemistry, but the idea was to link this to a pre-organized platform like this one, which is a trypsine, which could be properly functionalized with these iodo groups. Eventually, you can cross-link selectively this dye one step. You can put the red one or the blue one or the green one, and you can continue to play this game and eventually end it with this complicated trypsine grafted with a red one, a blue one, and the green one. So you probably see now the idea. Would it be possible by excitation, for instance, in the trypsine to have a selective energy transfer process from the red one to the blue one and to the green one, and then emission almost exclusively of the green one? Yes, you can do this, but first you have to be convinced that we have prepared the molecule. So the way to do this is to use proton NMR, because each of these dye have a signal which is diagnostic and quite representative of the blue, the red, and the blue one, and the green one. So the important part here is the proton-proton coupling constants of the proton localized on the double bonds. So it's in the order of 16 Hertz. So we are sure that in all these cases, first we get the good stoichiometry and all the confirmation of the double bonds are trans. What is the absorption? Again, the absorption is a linear combination between the absorption of trypsine, which is this big one here, of the red one, which is the absorption here localized around 540 nanometers, the blue one 640, and the green one. When we excited here at between 280 and 320 in the trypsine, so what we see is this emission. Most of the emission is coming from the green one. We have a little bit residual emission of the red one and of the blue one, but not emission at all of the trypsine. So this is quite interesting. So would it be possible to know a little more? Yes, we can, because we were able, of course, to prepare with the process that I have summarized in one of my slides, able to prepare a dye with two blue and a red one. So the blue one is dominant because of the absorption coefficient. So the solution appears blue, but it emits in the red. And you do see this is the spectrum. You do not see a little bit residual emission of the red one, but only emission of the blue one. Then you can calculate what should be the rate constant by determining, for instance, the quantum yield of the residual excited state lifetimes. You can do exactly the same with the 2 green and 1 blue one. So this appears green, and it emits almost exclusively in the red and near infrared with a little bit residual emission of the blue one here. Then you can calculate by determining the quantum yield of this one and this one, what is the rate, and you see it's really fast process in its picosecond time scale. And endly, you can also prepare the 2 red and 1 green one. Now you see here that you have a dual emission. This is roughly 10% of the emission, which tell you by calculations that the rate is not as fast as it was in the other way around. So the conclusion is the following. Yes, we have a directional energy transfer process, because the emission transfer from the red one to the blue one is much faster than the emission from the red one to the green ones. And you have direction to transfer your energy. Of course, this in solution is not useful, but if you can, this is a project which is still ongoing. If you connect this to a nanoparticle and you put this on a surface, then you can expect to use the energy transfer to generate motion on the surface. You do not need necessarily to have something which is two-dimensional. You can use something which could be completely linear. The idea is also to use the bridge as something which is able to absorb the photon, because there is no reason why the bridge could not participate in the energy transfer process. So, so we were able to construct this kind of molecule. There is different way to construct this. It's quite, as you might expect, quite a lot of energy to increase the number of modules here. And the way we use it is to construct everything on the red module, and then we cross-link this to the blue one, which is now, as you can see, an iso-indole-based red emitter. So we have all these nice molecules where we have the blue one, which is linked with different modules to the red one. And of course, the challenge was to study the photophysics. So the absorption spectrum is something that you expect. So different length here. When you increase the length of the linker here, you do not expect something different from the absorption of the red and the blue one. This is exactly what we observe, no modification. This is the blue one, this is the red one. And of course, what changed here is the absorption of the bridge, which is symbolized by this models here. You see this is increasing because the delocalization is increasing, and you have a bathochromic shift of the absorption of the bridge. When you excite it here, so this you can see, you get emission, really efficient emission of the red part, and you have no changes of the quantum yield by increasing the length of the molecule. When you excite it in the red one, then what you expect is energy transfer to the blue one, but this should be dependent on the length between the red one and the blue one. That's exactly what you observe. You have a little bit residual emission, which is increasing by increasing the length of the spacer. So the energy transfer here, these are the order of magnitude is a little bit decreasing, but still, with molecules which have roughly 50 angstrom length, you still have quite 80% energy transfer from one module to the other one. So you can determine what is the rate of your energy transfer process versus the length of the edge donor to the acceptor here. And you can see that you do not have any exponential dependence. So this tells you you have not a pure through-bond process, but you do not have a dependence on R at the power -6, R being the distance between the donor and the acceptor. So this is not also a pure Foster. So in this case, you have two processes. You have a through-bond process and a through-space process which is occurring. So is the concept of using the linker as an energy absorbent working? Yes, it is also, because when we excite it inside the bridge, so the bridge around roughly here, the excitation 440 nanometer, you do see a little bit emission of the red one and a little bit, and a lot of emission of the blue one. So this tells you that you have two mechanisms which are occurring. Energy is transferred to the red one, but also to the blue one, and then the red one is transferring its energy to the blue one. Okay, so of course you can use linkers, to absorb photon and to generate the same process. And we, in the transient absorption spectroscopy, we have two rising times, the one which is localized on the red one and the one which is localized on the blue one. Of course, there is no reason why not continue this game, because you had at the end fluoro groups here. We were able to functionalize this fluoro group with pyrene, which is more absorbent in the near UV, and then you have the same process as before. Excitation is a prior, cascade energy transfer, really efficient. This was the beginning of my presentation, to the red one, and then energy transfer from the red one to the blue one. And this is really active in solution, but also in the solid state, and in particular in polymeric films. You see the idea of using this in devices. Now I switch a little bit on redox properties of these molecules. We were able selectively to functionalize the body P with one arene, so this is phenyl, or two arenes. Clearly what you see here are two reversible processes versus ferrocene in solution. This is dichloromethane. This is the radical anion, and this is the radical cation. If you change the electrodes, the solvent, supporting electrolyte, you can also generate the dianion in a reversible way and the dication here. So we will focus now on these two species. What is interesting to see, you see that we get by substitution, the fluorine by an aryl, we have a translation just of the two redox potentials by roughly 100 millivolts by monosubstitution, and not far away from 200 millivolts by double substitution. So, of course, the idea is because we were able to change the chemistry here, we were also able to generate thin films, which are not soluble, for instance, in acetylnitrile because of the presence of these paraffin chains here. So in collaboration with Alan G. Bard at the University of Texas, we were able indeed to generate light just by using electricity. As you might expect, we can generate the radical anion and the radical cation in a film, and then there is no reason why these two species do not react together to generate an excited state, and you generate light. So this is chemioelectroluminescence, and indeed it has a setup where you can follow, put electricity inside your film and follow if light is emitting. So what we are doing here, we reduced our film, okay, and 100 milliseconds after, we oxidized it, and we follow if light is emitting. So this is exactly what happened. We reduce the film, we oxidize it, and you have a peak of light. And this is continuing, and you have no degradation of the system. We run this over more than 1,000 cycles. So this is quite interesting, because what is important is to see which kind of light is going out of your system. So this is the photoluminescence of what that we obtain. This is the electroluminescence that we have observed. So we have a dual emission. One is clearly very close from the photoluminescence in solution, and the other one is something new. Okay? If we use a quencher here, which is a triplet quencher inside our film, these near-infrared luminescence do not appear anymore. So what we believe is that the following is happening. Of course, we generate a singlet excited state, which emits, as usual, like in solution, which has a wavelength really close from the one that we observed previously. But we were also probably able to generate an annihilation between the radical anion and the radical cation. Then you generate a triplet excited state. This triplet excited state could be annihilated, generate the singlet excited state, and then you have relaxation. Or this triplet excited state could also directly relax to the ground state, and then this light is emitted. And we believe this is emission of light of the triplet of the body part. Of course, there is then a possibility to organize this as a sandwich organization on a surface. Why not putting, for instance, this organic layer? So we are dealing here with only organic material. We do not have any heavy metals, transition metals. Why not putting this in between a Hall transporting layer and electron transporting layer, something which is transparent and some contacts? Okay. The problem with these flat molecules, depending on the substitution, these molecules has also a big tendency to make aggregates. And if you generate aggregates, of course, you cannot have a system which emits pure light. So the idea here is to indeed dope a well-known energy donor, which is an aluminium Q3 matrix. And we use body pi, we dope this matrix with body pi, and what is expected when you generate your exciton on the aluminium matrix, then you will generate an energy transfer, and you have seen previously that this could be really efficient. You transfer your energy to the body pi, which then generate an excited state or excitant for physicists, which relax to the ground state. So is this concept working? Yes, it is for the following reason. So this is the absorption of this body pi. So now you see a terpyridine. Don't ask why a terpyridine, but this is why we started with this one indeed. So you have new transition here, which are pi-pi transition of this polyaromatic system. This is the second excited state of the body P, and this is the first excited state. And you see here we have a really nice overlapping between the absorption of the body P and the fluorescence of this aluminium compound. So of course, in this case, the overlap is perfect and the energy transfer should occur. And this is exactly what we observe. So this is an OLED which has been generated only with aluminium Q3. So it's green light. When you dope this with 0.7% of a body pi, really low amount, you switch from green to orange light quite easily. And this is confirmed also by the spectroscopy. So this is electroluminescence of your aluminium compound. In your doped material, you do not see any residual electroluminescence of the aluminium compound, but only electroluminescence of the body pi, which is overlapping with what you expect as photoluminescence in solution or in a thin film in the absence of the aluminium compound. Of course, we have played a little bit with this concentration because, as mentioned before, body pi likes to aggregate from this part. You have pi-pi interactions, which are quite favorable. So in this case, if you increase the concentration of the body pi inside your layer, you might also generate dimers, oligomers, and you then switch your light from the monomer to a dimer. And indeed, if you increase the concentration from 0.7% to 7%, then you have electroluminescence, which is yellow, which is not pure because you have a little bit emission of at 640, which is a dimer. If you increase the emission to 19% of body pi, then you see only a little bit residual emission of the monomer, but you have a lot of emission of the dimer, and the light is now red versus yellow before. So of course, and I will finish my presentation with this. We use this, of course, also in solar cells, because of course, we were able to change the color, as mentioned before. We can, just by putting a double band here, you go to a magenta compound, which emits in the orange, and if you do this 2 times, you go to a blue compound, which emits in the red. A priori, we are able to put here what we want, and we start with the iodo group. And of course, as you might expect, if you have an iodo, you can generate an acid, and you can then use this in DSCC solar cells, but I will not speak about this. The idea here is to avoid formation of dimers, trimers, oligomers, and one way to do this is to substitute the boron. If you increase the steric encumbrance around the boron, then you generate molecules we do not aggregate anymore, which could be nicely could be used to process in thin films. Molecules are highly soluble, and this is something what we are looking for if you want to use this in bulk heterojunctions. So what is important here, we do not use DSCC cells, so we have no relay, we have no solution, we only deal with bulk material. And of course, the idea is to use body pies, so cells which do not use transition metals or any toxic materials. So the idea is really simple. Would it be possible to generate solar cells where we have an active layer, which is indeed a blend between our body P and PCBM, so an electron acceptor, which is a C60. This is, at least this is the problem. And we can contact this with some metals, which is aluminum or calcium. Really simple system. So this just a little bit spectroscopy. So this is the absorption of the magenta in solution. This is the absorption of the film. So we confirm that we have no aggregation inside the film. This is true holds true from the magenta, but also for the blue compound. When we generate the solar cells here, this is the photocurrents that we generate versus the wavelength of the monochromatic light that we use. And you see the current photocurrents generate an absorption spectrum here, which is the one that we have in the thin film or in the solution. So we are sure what is active here, of course, the body pie. We have, of course, a new absorption here, which is the absorption of the C60, which is used as an electron reservoir. The concentration is quite high. So it's at least 2 times the concentration of the body P, which could be a problem. But the absorption is around 400 nanometers. So this is the current density that regenerates versus the voltage. This is in the dark. This is under irradiation, so we have a dark current. As you see, the VOC here is in the order of 0.8 volts. The fill factor is quite low, but the efficiency is in the order of 1.3%. Conversion of light to electricity. And standard conditions which are given here. Okay. When we mix 2 dyes together, it's quite easy to do, the blue one and the magenta, then the absorption corresponds to the mixture, plus this absorption which is close from the C60, and the power conversion in these conditions were in the order of 1.7%. So at that time, for bulk heterojunction, it was the best record. Now, of course, it has been bet really easily by many groups in the world, and roughly we are not far away from 5% now. So pure materials. So this is the demonstration. If just by switching from an iodo to a bistyrene with some greasy change here for solubility reasons, we have a really nice, so it's recent results that we have obtained in collaboration by the group of Jean Roncalli at the University of Angers. And you do see that the conversion here is roughly around 5% with current density in the order of 8.5 milliampere per square centimeters. So this was the last scientific slide. So I have no conclusion, but you can see really nice trends, what we are doing. So these are the people which were involved in the students from my groups here. So most of the work has been developed by Christine Gauze, which has an assistant professor position at the University of Dijon. And also by the wire has been developed by Alexandre Raffeler, which is postdocing in the US, and also by Jean-Hubert Olivier, which is also in the US. And these are students which are still working on this. Jean Roncalli has been alleged before. These are the people which made indeed the fast spectroscopy either in Newcastle with Antonia Riemann or Sebastiano Campagna at the University of Messina. And Pascal Ruteillot at GCEVET determined all the extra structures. And CNRS is acknowledged, of course, for part of the money. So, and I would like to thank you for your time.
So we have time for questions.
No, Raymond, I'm not familiar with Baud IP. So you said that Baud IP, boron Baud IP, it's a sort of porphyrin, half porphyrin. So does 3/4 or full porphyrin of boron exist? And if yes, what's the difference?
A few quarter? What do you mean?
3/4. I mean, 3 spiral.
But then the problem, if you have 3 spirals, you have, because we started with the dipyromethane without the boron. Yes. So this has a quantum yields of roughly 1%, less than 1, because it's not rigidified. So if it's a flexible sign-in, and this has many ways to desactivate by a non-radiative way. So then if you have 3 spirals, you need to stabilize it. It must be flat, rigid, in order to have really high quantum yields. But you also notice the quantum yields here are roughly over 90%, which is not the case of porphyrins. Porphyrins are not as usually. And platinum porphyrins is roughly 18%, but it's emitting from the triplet. This is roughly only singlet emission.
You mentioned the fact that you used your Baud IP in the DSCC. How does it compare with heterojunctions?
It compares, it's more complicated to proceed for us because we are not expert in DSCCs in dyes, but with the blue one, we got 5%, which is not as impressive as the numbers that we saw this morning with transition metals. But I guess we are more excited by bulk heterojunctions because there are less people inside the field first, and it's quite easy to proceed.
So you show the electrochemiluminescence in solution. Do you have any evidence of excimer formation because you generate anion and cation, and they can interact and?
The interaction in the film between a radical...
No, in solution, in the first part of the presentation.
If you aggregate in the ground state, you generate excimers, then your absorption is shifted batochromically. You can see this quite easily, meaning the absorption is not normal. You have a new absorption in the near infrared. And what is more important, when you excite it in the singlet or the dimer, you decrease the quantum yield, and your excitation spectrum does not fit anymore with the absorption. So if you have aggregates in solution or films, two things are really important. Quantum yields, excited state lifetimes also, but the excitation spectrum is not overlapping anymore with the absorption.